Okay, so good evening, everyone, and I welcome you all to today's live session of Nonlinear Vibration, NOC25 ME57. And this course is being taught by Professor S.Q. Dwivedi, IIT Guwahati, and I am Rasha Diti Ranjan, NPTEL PMRFTA from IIT Patna. And I'll be taking the live sessions of this course, and we'll be solving questions and understanding the concepts of nonlinear vibration that will be helpful for you to solve the questions. And Abhimanyu, as you asked a question earlier that about the assignment questions, so I would like to tell you that almost all the questions are taken up from whatever has been taught in week one. However, there are certain questions that are general, and if you'll attend this live session, you'll be able to answer those questions. Okay? Okay. Okay, Manu, I think you left the meeting in between. So I was telling that almost all the questions are from whatever has been taught in the lectures. However, there are some questions which are from the general concepts of nonlinear vibrations, and that you will get to know as we will proceed with this live session. As I have tried that I include all the questions that will be required for you all to solve the questions. Okay, so we'll start. Okay, so coming on to first question, which comes from the very basic concept of the difference between a nonlinear system and a linear system. So we'll talk about what and how can we know that whether a system is linear or non-linear. Like for example, if I talk about the Duffing oscillator, which is not Duffing oscillator, actually a spring mass system with damping. So we write the equation of motion as follows, wherein we have a support, a spring, a dashpot, and a mass m. This is C and this is K. So if I talk about that whether this equation is linear or non-linear, so if you'll see, yes, this is a linear equation. It is easy to solve analytically, and you have must have been taught about the analytical solution of this equation in your vibration course, mechanical vibration course. And if you have not been taught, maybe further as you will go up with your studies, you'll get to know. So, okay, okay. So this is your equation. So this is a linear equation. It is easy to solve. Now coming on to why do we need to know that whether a equation is linear or non-linear? Right. Because for a linear equation, we know there is analytical solution. Right. And from this analytical solution, I can get the continuous form of its solution. Right. And if I know the continuous form of the solution, or I can say the closed form of solution, if I know about an equation, so then I can easily find out how the system is going to behave depending upon at what time I want to know, at what value of k, at what value of c, and at value of m. But when I talk about a non-linear equation, see, it becomes difficult, right? Like let us take example of a simple pendulum, which we have been studying about since a very long time. There is a small bob of mass m, and then there is this thread which is inextensible, correct? If you people remember that the equation of motion is what? Theta double dot plus g by L sine theta is equals to 0, correct? Where theta is the angle from the vertical. Now, if you look, this sine theta is essentially giving a nonlinearity to the equation, right? Now, we used to calculate the analytical solution of this equation considering that theta is small, and so sine theta is nearly equal to theta, correct? But what if I don't consider this assumption? And essentially, it is important that we don't, because if you try to find out the value of theta for which this is applicable, you'll find out that the theta value is very small. And in practical applications, we don't work with these small of theta values. We consider larger values of theta, right? So if this assumption of linearity is not right, then what are we supposed to do? How to find a solution of this nonlinear equation? Now, this is a transcendental equation, and it is indeed very difficult to find out a solution. However, there are some researchers that have successfully found out the solution of this equation through their work. However, it is very mathematically extensive, right? So, what do? We prefer going into the approximate solution or either finding out a numerical solution, right? So that is why it is necessary that we know when we have an equation of motion that what kind of equation of motion it is, so that after that we'll know that how to deal with this problem. Like for example, even if the equation is non-linear, the order of non-linearity will let us decide that whether we should go with the numerical solution, we should go with the analytical solution, we can go for the superposition rule, or what do we have to apply? Okay, so coming on to the question, we have this equation which is u double dot plus omega naught square u minus epsilon u dot. Now this in general is known as a Rayleigh equation. And as you'll proceed further with this course, you'll get to know that this Rayleigh equation is very important and it brings about a very important concept of nonlinearity. Okay, so how do we find out whether this is linear or nonlinear? Okay, so we'll go by the basic method. I'll try to explain by the basic method. However, I expect that as this course proceed, you people are able to identify just by mere looking at the equation whether it is linear or nonlinear. Okay, so coming on to how. So there are two ways. Okay, maybe I can write here only. There are two ways, which we also call as the superposition rules, which contains the first rule, which is the homogeneity rule, which says the homogeneity rule says that, for example, we have a function f, okay, such that x of t gives me f of t. Okay, now if I multiply alpha with this x, it is going to give me alpha into f of t. Okay, now if I try to apply this to my equation, you see for x of t, or let us for easiness assume u of t, we have f as what? U double dot. Okay, this is our f. Now let us replace u of t by alpha u of t. What are we going to get? Let us say this is f dash alpha u double dot. This is your f dash. Now, if I take alpha common from this equation, what do I get? Right? Now, tell me one thing. Is this f of t? Is this equal to f? No, this is not equal to f. As you can see, there is this alpha square here. Right? Now, this alpha square is not letting the homogeneity rule be true for this equation, which means that this equation is nonlinear. Okay. There is second rule also. We'll just study the second rule for the sake of knowing. And although if one of the rule is not satisfied, it is simple that you can conclude that the equation is nonlinear. Okay. Coming on to the second one, which is the additive property. Okay. So the additive property says that if x1 of t is going to give me f1 of t and x2 of t is going to give me f2 of t, then x1 of t plus x2 of t is going to give me what? F of, which is also equal to f1 plus f2. Okay. So for example, if I put x1, I get f1. If I put x2, I get f2. So if I put x1 plus x2 in the equation, I should get something which will be equal to f1 plus f2. Okay. So if I try to do this with the equation, so what am I going to get? If I use u1, I'll have u1 double dot. This is the first equation. Second one will be u2 double dot. This is the second equation, correct? Now, what was there? We had to replace, right? We had to replace u with u1 plus u2 in the main equation. So what am I going to get? I'm going to get u1 plus u2 double dot omega naught square u1 plus u2 correct? If I simplify this, correct? But this is what? This is your f of u1 plus u2. Okay. But this should be equal to what? F of u1 plus f of u2, right? For the additive rule to follow. But you will see that this is not equal, right? Because if I write f of u1, f of u2, what am I going to get? I'll get, right? So additive property is not true for the given equation. So what do we get? Even the additive property is not applicable and your homogeneity rule is not applicable. So then what do we conclude? We conclude that the given differential equation is nonlinear as it does not satisfy the superposition rule. Okay. So here B is the correct answer. Okay. I hope uh, this is clear. And so by these rules, you can anytime see whether your equation is linear or nonlinear. And with time, as you'll deal with nonlinear equations, you'll see that it will become easier for you to just look at the equation and conclude whether it is linear or nonlinear. Okay, I hope it is clear to everyone. Let us jump to question number 2. So question number 2 is essentially a case of a linear system, but you had questions for this. So I thought that I'll just give a brief about what is transmissibility ratio. Okay, so now if I consider that there is a spring mass, okay, that there is a spring mass system which is attached to a support which itself is vibrating as y sine of omega bt. Okay, so this is a function of time. It is having a sinusoidal oscillation, and then my mass m is also oscillating as x of t. Okay, so if I see this, if I try to find out the equation of motion of this mass m, what will I write? I will write m x double dot plus c x dot minus y dot and plus k x minus y is equals to 0. Right? This is a simple linear case, so I'm not getting into the depth of how the equation of motion is evaluated. However, you can try getting it by the force balance method. Okay. So this is essentially the equation of motion, right? Now, considering that my y is oscillating with time like this, okay, so I will get a ratio, okay, a ratio of the amplitude of oscillation of my mass m and the oscillation of my support, which we say as x by y, and it is written as under root 1 plus omega b by omega n whole square divided by 1 minus plus 2 square. Okay, so this is your transmissibility ratio. This is what we call the transmissibility ratio. Now the question is how and why is it important, right? So if you see correctly the diagram, if you try to interpret the diagram, so you can see that there is this support, right, which can be a floor on which a machine is operating, correct? Which could be your the floor of the train you are traveling in, the bus you are traveling in, right? So this is essentially a support. Okay. So if your support is actually having some kind of a vibration, okay, that vibration is going to get transmitted to you, or that vibration is going to get transmitted to this mass m, right? So if that vibration is going to get transmitted to this mass m, it is important that we know that how the mass m is going to behave, right? Now, for example, let us say that what if the support is oscillating with an amplitude of 20 and the mass correspondingly is vibrating at an amplitude of 40? What is going to happen? It's going to create a lot of chaos. Will you ever prefer to travel in such a vehicle or remain in such an environment? It's not possible. Specifically, if we talk about machines, if machines are going to operate in such condition, they are going to have fault, they are going to get ruptured, or they are going to not be able to give the efficiency it is required. Okay, there is no problem, Abhimanyu. After this session, the video and the PPT will be shared with you. Okay, you must have got a link for the document wherein you'll get both. So you can watch the video later and you can read this PPT also. This PPT along with the solution will be given to you. Okay, I hope it is clear. Okay, so this support is essentially going to affect how the mass is going to behave, right? So if there is a lot of vibration going on with the support, the mass is also going to get that oscillation, and because of that, it is going to cause trouble, right? So it is important that we know that how the oscillations are being transmitted to the mass m, right? Because that we should control that how and what amount of oscillations are being transmitted, so that we know that what are the safer regions in which we can operate a particular kind of machine, or where a particular human can work, right? So that is why transmissibility ratio is important, because it is going to give you a ratio of the amplitude of oscillation of your support corresponding to that of your mass, right? So let us talk about what the question says. So the question says that for a single degree of freedom system, if omega by omega, okay, here it should be omega b. So omega b by omega n is under root 2, then the transmissibility ratio. So what do we have to do? We have to simply put omega b by omega n is equals to under root 2, right? So if you will put here, what will you get? You'll get right. So solving this further, you'll get what? This will go to 1, right? In a negative sign, whose square will be positive 1. So it will again be, okay. So the transmissibility ratio will come out to be 1, which means that here the answer is going to be remains the same, right? We'll get to know that when omega b by omega n is equal to under root 2, which means that the ratio of the frequency at which the support is oscillating to that of the natural frequency of the spring mass system is equal to under root 2. In that case, the transmissibility ratio is actually independent of the damping parameter, and that you can see over here also, right? So if you see this graph, this I have taken from the book, which you can get in any of the mechanical vibration book. Okay, so here the frequency ratio region is divided into two halves. One is less than under root 2 and the one greater than under root 2. So here you can see for transmissibility, sorry, the frequency ratio, omega p by omega n less than under root 2, what do we have? We have the transmissibility ratio greater than 1, which means that whatever will be the amplitude of support oscillation, whatever will be the amplitude at which your support is oscillating, it will always be less than that of the amplitude of system oscillation, which means that your support oscillation is going to get amplified for the system oscillation, right? It will get amplified and give the system oscillation. Further, you can see that with the value of your damping parameter, so as the damping parameter value is increasing, transmissibility ratio is decreasing. Okay, so even if you have, when you are designing, for example, something, even if you have the ratio less than under root 2 and transmissibility ratio greater than 1, you can still try to control the oscillation or bring it back near to 1 at least by increasing the damping parameter, right? Now if I consider for omega p by omega n greater than under root 2, we have the transmissibility ratio less than 1, right? So which means that if my ratio of the frequency is greater than under root 2, my transmissibility ratio is always less than 1. So anyways, it is good for absorbing the vibration, right? To be used as a vibration absorber, because in that case your whatever amplitude your support is oscillating, that is not going to get transferred into your system, right? And if you see here with the value of damping parameter, as damping parameter value is increasing, the transmissibility ratio is actually increasing and not decreasing. Okay, so even if you have a transmissibility ratio near to 1, for the ratio of a frequency greater than under root 2, what do you have to do? You have to decrease the value of damping parameter so as to get a lower value of transmissibility ratio. Okay, I hope it is clear. So this exercise was wholly designed in order to know that how the system is going to behave, right? When you have a support oscillating and your system is mounted on that support, and then in that case, how would you see or how would you design the system in such a way such that you get lesser transmission of the vibrations. Okay, coming on to the third question. So the question says that the spring force is given as F is equals to 10x plus 17x cube. Then the spring is, and then there are different options. So see, in case of a linear system, we used to study that F of spring was equal to K into X, where K was what? Stiffness of spring, and X is not extension, actually, it should be the deformation. Correct? We used to show the linear spring something like this, right? So if I try to plot the behavior of a linear spring, what will I get? This, and the slope will be equal to K. which is the stiffness of the spring. So we see what? We see that there is a linear relation between the spring force and the elongation or deformation x, right? So this is the case of a linear spring. But now since we are studying about a non-linear system, so if you see, if you take a pen which has a small spring and you try to compress it, you will see that as soon as you try to compress it, when the compression increases, the force also you have to apply higher, a bit higher, right, for to further compress the spring. Or when you try to take a rubber band and try to extend it, initially it is easy to extend it, but after some time it becomes very difficult, like you have to apply more force in order to get even a smaller deformation, right? Why this happens in the real world? Well, that is because of the stiffening of the system, or we can say that non-linearity of the system. During the linear zone there is a constant relation, right? But as soon as the linear zone, we get out of the linear zone, the behavior gets nonlinear, right? Now, nonlinearity can be of two types, right? It can be of softening type or it can be of hardening type. Like for example, the equation that has been given, which is f is equals to, let x is equals to 1. Okay. Now what will be the value of f? 27. Now if I talk about a linear spring, how much value will it be? Just 10, right? Now, if I talk about the kind of spring that has been given to us, the behavior is something of this sort. Uh, I'll try to make a much exaggerated view, something of this type, right? Because the value that we are getting is higher, just 27, right? So this behavior is that of a hard spring. Why do we call it hard spring? We call it hard spring because as the deformation increases, it becomes difficult to get the same amount of extension for a particular force, right? You have to apply more force to get a particular oscillation. So this is your hard spring, right? And if I talk about what if there is a minus instead of plus, we have, right? So if you calculate the force will come out to be negative, right? Force will come out to be negative, which is actually not possible in physical systems. But if it is coming out to be negative, you can understand what is happening. The system is actually getting unstable, right? The system is actually getting unstable. So the behavior is somewhat like this. This is your soft spring. Okay. So you have a hard spring, you have a soft spring, right? And on the basis of these two kind of springs, you are going to get how the physical system is going to behave, right? Now, we used to use a linear spring when we used to deal with linear systems, but as you have now entered into the nonlinear domain, you can get a system which has both hardening and softening relation. Yeah, like we can have the spring force something of the sort 5x minus 17 x cube or and plus 25x to the power 5, something of the sort. You can get it, right? And depending upon this relation, you can know whether the system is behaving in a hardening way or softening way. Now, this hardening and softening, as I'm saying, what I mean to say by this is that hardening means as you increase the deformation, like if you take the spring out of a pen and then try to deform it by applying a compressive force, you'll see that it is easier initially, and after a certain time, it becomes difficult, right? So, in that case, it's a hardening system. Hardening means as the deformation increases, the force that is required to create a certain deformation also increases, right? While in case of a softening system, the opposite is going to happen, okay? Which means that initially it will be easy to cause the deformation, and after some time, like deformation, it will become easy, right? So even for a small amount of force, you can have a large amount of deformation, right? So it will depend upon the kind of spring that you are using. Now, when we are trying to do application of any kind of application, uh, you can say for creating a spring mass system, for creating any kind of actuator, for creating any kind of apparatus, we need to decide what are the requirements of my system, right? For example, I want my system to be of a certain kind, it should behave in a softening manner, it should behave in a hardening manner. Then I would select my spring or my material of this type, right? If you see any kind of continuous materials, you'll see that those continuous material actually show non-linear stiffness only. Like for example, if you'll see a cantilever beam, right? So like if you have a cantilever beam of this type and you apply force over here, F, you'll see that as F increases, it becomes difficult to show the deformation. Yeah, it becomes difficult. You see, if you have a beam, like for example, if you have a scale and then you try to deform it like this, you can deform it up to a certain amount only, right? After that, it becomes difficult. Although if you are going to apply a lot of force, that scale is going to get broken. If you try with a metal scale, you'll see that how this is going to happen. Okay, so I hope you people are done with the concept of hard type of spring and soft type of spring. And depending upon the hard type of spring and soft type of spring, you remember the spring mass system we used to deal with? Spring mass system we used to deal with mx double dot plus cx dot plus kx is equals to 0. So what is this? This is a linear spring. Okay, the variation is linear, right? Now this spring mass system introduced with a bit of nonlinearity, like beta x cube, is known as the Duffing equation. Okay, we call it as a Duffing equation. And depending upon the value of beta, we are going to further call it as a soft Duffing oscillator, hard Duffing oscillator, or soft Duffing equation, hard Duffing equation. Oscillator we usually use when this is not zero. This has some value, f sine omega t or f cos omega t. We have some kind of oscillation that is already present in the system. But for this case, if beta is positive, we have a hard Duffing equation. And if my beta is negative, we have a soft Duffing equation. Okay, which means that if my beta is positive, as soon as my value of x is going to increase, it will become hard, to get more deformation. While in case of a soft Duffing equation, as my x increases, it becomes easier to get a particular deformation. Okay, I hope it is clear. Coming on to next question. Okay, so this question says that the response of the system is given as the equation is giving, then the response type of the system is. Okay. So coming on to z is equals to right? Before coming on this, let us consider a easier case first. For example, if I give you a equation like x is equals to 2 sine of 2t. Okay, this is the response of a system. So what do I understand? I understand that this is my amplitude and this is my frequency, because any kind of a response is in general written as a cos omega t, where a is my amplitude and omega is my frequency. Correct? So here, this is the amplitude and this is the frequency. So the response is that it is going to behave in a sinusoidal fashion with a frequency of 2 and an amplitude of 2. Okay. Now if I replace it with something like this, 3 3 cos of 4t plus 4 sine of 4t. Okay. So there are two terms, right? There are two terms. One is a cos term and another one is a sine term. Okay. So how will I know that what is going to be the frequency and amplitude? Here is one thing is clear, that the frequency is going to be 4, right? Because in both the terms the frequency is 4. Okay. But what about the amplitude? So as you can see here, one is cos and another one is sine. So the amplitude is going to be nothing but under root of, which is equals to 5. So for this equation, we'll again have a, okay, here I can write also, here the behavior is going to be periodic. We are going to have a periodic solution, right? Periodic behavior. Now for this again we are going to have a periodic solution. Here there are two terms that are contributing towards the solution of the system. Okay. So this is again going to be periodic, right? Now coming on to, okay, I know this is periodic, but what about the given equation? Is this periodic or how is it going to behave? Okay, so first you see the options. The first one is the periodic, which we know how is it going to behave. Periodic. Periodic solution is going to be something like this. Okay. After a certain period, the response value is going to be the same. Okay. So then we say that it is a periodic oscillation. Coming on to what is chaotic oscillation. Chaotic, let us just not get into it. However, what I can say and what you can also understand is that this is never going to be chaotic, because chaos is a much difficult type of behavior than periodic. So how is this going to be? So then we have something called as quasi-periodic response. Okay. So for such kind of a system behavior, okay, where we have consecutive addition or subtraction of sinusoidal or cos kind of a behavior, which we can say periodic type of a behavior. So it can have multiple amplitudes, it can have multiple frequencies, right? So there is a rule that says that, for example, if some response z is equals to, for example, if there is a response something like this, and if we have omega 1 by omega 2 as a irrational number, omega 1 by omega 2 is as a irrational number, then what is going to happen? The behavior is going to be, nothing but quasi-periodic. It will not be periodic. Remember, if the ratio is irrational, if the ratio is rational, 1 by 2, 2 by 1, 1 by 3, 3 by 1, or anything of that sort, it is going to be not quasi-periodic. Okay, but if it is irrational, like for example, for the given question, if you will see omega 1 by omega 2, what is it? It is 1 by under root 2. Under root 2 is what? It's an irrational number, right? So we have the ratio of frequency as an irrational number, which means that the response is going to be quasi-periodic. And now if you'll ask that what is a quasi-periodic behavior, how it is different from a periodic behavior. So essentially what happens is that if you have this kind of a behavior, okay, wherein the frequencies, okay, the frequencies don't actually relate to each other in a rational way, okay, does not relate to each other in some rational number, okay. So in that case they behave in a quasi-periodic way. Now how is a quasi-periodic oscillation going to happen? So see, this is a periodic oscillation, this is a periodic oscillation. If your response is something like this, this is called as a quasi-periodic behavior. The frequencies are not in a rational product, right? So it is has a irrational number in between. So that is why this kind of a behavior, which is not periodic, not properly periodic, but not properly aperiodic. This is something in between. Okay, you cannot say that it is aperiodic. Okay, because aperiodic motion is what motion? Which is not at all periodic. This is not like that. This is something like you'll have an oscillation of this sort. You have periodic like this, right? For a quasi-periodic motion, you're going to see something like, then again it is going to repeat, something like this. Okay, but this repeat, repeat, repeating value is not going to be the same. There will be some variation, very small variation. Okay, and that is why this kind of a band-like behavior will be seen. Right? Like if a periodic oscillation, you'll get a simple circle or maybe a oval, something like this. Okay, one line. But in case of quasi-periodic motion, because this value is not same at which the value is repeating, you're going to see a band kind of a behavior. Okay, so we call it a quasi-periodic motion. As we'll proceed further with the questions and everything, we'll do some exercises in MATLAB and then we'll get to know that how the quasi-periodic motion essentially is. Okay, Deepu, can you please switch off your mic? Thank you. Okay, so the answer here is going to be quasi-periodic. Talking about chaotic motion, I'll give you a brief idea about chaotic motion. Chaotic motion is essentially a periodic motion and it is very different from a periodic motion. It is something we cannot be certain about. Okay, and it shows a very high dependence upon the initial condition. Okay, so we'll discuss about it further when we'll come to that example. Okay, coming on to question number 5. Okay, now from here I'll be introducing the concept of bifurcation. Okay, what is a bifurcation and how is it going to affect the system? So first we'll talk about the buckling of a beam. Okay, what is a beam? So there is this mass M and here is this rod here and it is under a compressive load, right? It is going to compress the rod. So this is what? This is essentially a beam, right? Now if I keep increasing the mass, you people must have learned in your mechanics of deformable bodies that buckling happens in a beam. Okay, so what essentially happens is if you keep increasing, okay, I'll write it. Sorry. what is going to happen? You know, there is a critical buckling load. So what happens is that after that critical load or at that particular load, the beam is going to buckle. So the beam, when it is going to buckle, something this will happen. The beam will buckle. Okay, will become like this. Or the beam can go like this also. Right? So any of the both can happen. It essentially depends on the moment of inertia actually. But if I consider that the cross section of the beam is a square, okay, both the dimensions are same in the aerial view. In that case, any of these cases, case 1 or case 2 can take place. Any of the case 1 or case 2 can take place, right? So if that is the case, how will I know which one is going to happen? And how is this possible? For a linear system, I know that there is going to be like one fixed point, right? For a linear system, fixed point is what? Fixed point or equilibrium point is where the system is in equilibrium state. All the forces are balanced. There is no acceleration in the system, right? The system is not actually, we cannot say it. Even if it is moving, either it will not move or if it is moving, it is going to move in a constant velocity fashion, right? So how is this like essentially there was one equilibrium state. Now there are two equilibrium state. So what actually happened in between? Okay, so for that reason, we'll first have to study what is bifurcation. So as the name bifurcation suggests, that bifurcation means there is a bifurcation, or you can say that there is some breaking, okay, of the points. Like for example, one point is broken into 2 points, and now the both have their own paths, right? They are getting bifurcated. Like if you're going on a road, it bifurcates in two different ways, right? Something of that manner. So for a physical system, if we change the parameter value, what are parameters? Okay, so for example, for a spring mass system, M, C, and K are my parameters, right? This is what we call as parameters. So what happens is that if I change the value of the parameter, the system behavior is going to change, which is evident if you try to simulate a spring mass system also, right? If you change the value of stiffness or if you change the value of your damping, you'll see that it will either have a critically damped oscillation or it is going to have a underdamped behavior or a overdamped behavior. Anything can happen, right? Similarly, for a bifurcation, wherein we consider the equilibrium points of a system, we see that as the parameter is varied, the number of equilibrium points for a system is going to change. The number of equilibrium points as well as the type of the equilibrium point. Types means whether it's going to be stable, whether it's going to be unstable. You know what is a stable and unstable equilibrium point? Equilibrium point can be stable, unstable. Everyone must have gone through the concept. For example, we have something like this, a valley, or this, right? We have a ball over here, and we have a ball over here, right? If I take this ball and displace it, what is going to happen? And it is going to have air drag and friction. Yes, we are not considering an ideal environment. We are considering a physical environment. Okay. If you make a value of this type and you like take it and perturb it by some amount and then leave it, what is going to happen? It is going to oscillate and again reach to the equilibrium point. Equilibrium point, all the forces are balanced. Okay. So it is again going to reach where it started. So this is a stable equilibrium point. While for this case, even if I give a very small negligible amount of perturbation to it, what is going to happen? It is never going to return back to its position. Never. However, at that particular point, all the forces are balanced. At that particular point, at the tip of the mountain, the forces are balanced and the ball is in complete equilibrium, right? So it is essentially an equilibrium point, right? Because all the forces are balanced, everything is balanced. It is in a static state also, right? So it's an equilibrium point. But even if I displace it by a very small amount, it is never going to return back to that equilibrium point. And that is why we call it as an unstable equilibrium point. This is my unstable equilibrium point, right? So with the change of parameter, my number of equilibrium points and the stability of the equilibrium points, both are going to change. And the study in which we deal with this is known as bifurcation. Okay. So I'll be talking about two, three main types of bifurcation, and as we'll proceed with the study, we'll also learn about the more difficult types of bifurcation and even the this dynamic kind of bifurcation also. Like here, we'll be studying only about the variation of the equilibrium points, but there could be dynamic bifurcations as well, wherein there will be a change in how the periodicity of the system is going to be, the periodic behavior, the chaotic behavior, and everything. Okay. So coming on to the first and the simplest kind of bifurcation, which is your saddle node bifurcation. So if I talk about the normal form of the equation, it is something of this kind, x dot is equals to r plus x square. So if I want to find out the equilibrium point or the fixed point, what will I do? I'll do x dot is equals to 0. So I'll get x square plus r is equal to 0. Now this is just easy maths. X is equals to plus minus under root of minus r. Okay. So you see that for under inside the under root there is minus r, which means that if r is less than 0, only then a equilibrium point will exist. If r is greater than 0, the equilibrium point will not exist. Correct? And if r is equal to 0, only one equilibrium point will exist. So we'll try to make the figure x dot x. Okay. Now we try to plot for all the three cases r less than 1, r is equal to, sorry, this should be r less than 0 and r greater than 0. Okay. What I know is that for r less than 0, there are two equilibrium points and they are going to reside on both halves of the x-axis, right? One will be positive, one will be negative and of the same amplitude. Okay. So let us suppose one is here, other one is here. For r0 in the center and for r greater than 0, no fixed points. Not talking about the stability of the fixed point. Okay. So the theory says that if I talk about this equilibrium point, okay, for this equilibrium point, if I try to calculate the value of x dot, okay, for this equilibrium point, uh, the first case, I'm talking about this equilibrium point. So if I try to calculate the value of x dot for my r or x greater than the value of the fixed point. What is going to be the value? You see here, x dot is equals to r plus x square, right? Now I'm already taking the value of x greater than r, right? So I'll see that the value of x dot is going to be positive and it will keep on increasing in a square fashion, right? Because you can see x dot is related to x square. So as x will increase, we'll see a well type of behavior, right? So it will be something of this type. Now, if I talk about x less than under root of r, you will see that the value is less than 0, right? Like this and like this. This is how it is going to be. Now, talking about the stability. So we say that when x dot, which is your velocity, is greater than 0, what is going to happen? If at a fixed point the velocity is greater than 0, what is going to happen? Or near to the fixed point. If it is greater than 0, it means that it is going to take my particle away from the fixed point, right? So here, if I try to make the direction of where my particle will go, it will go here, right? And if I talk about here, my velocity here is negative, right? But I'm on the left side of my fixed point, right? So my negative velocity is going to what? Again take me away from the equilibrium point. So the direction of arrow is going to be like this, right? Now if I come here, if you'll see, if I talk about this point, right? You'll see here I am on the right side of my fixed point, but my velocity is taking me towards the fixed point, right? So the arrow is going to be like this, right? And similarly, here also the arrow is going to be like this. I hope I'm clear and there is no doubt. So now, if you can see that for this fixed point, I'm always approaching my fixed point, which means my fixed point is stable because I'm always approaching it. While for this fixed point, as you can see, I'm always going away from my fixed point. And hence, this fixed point is unstable, right? So for r less than 0, I have two fixed points out of which one is stable and the other one is unstable, right? Now if I talk about r is equals to 0, here how the behavior is going to be? Simply this graph will shift in the upward way, na? Like this, like this. And here, if you'll see for r is equals to 0, what is happening is that as my value of r is increasing, right, and as soon as it reaches to 0, my both the fixed points, one stable and the other one unstable, come together to form a single fixed point, which is stable on this side and unstable on the other side. So this makes it a half stable fixed point. Why half stable I'm saying? Because if I approach from this side, it is going to take me to the fixed point. But if I approach from this side, it is going to take me away from the fixed point. And that is why it is known as a half stable fixed point, right? Okay. And as you can see, for r greater than 0, I don't have any fixed point. So if I try to plot with value of r, what do I see? Okay. something like this is happening. This is r is equals to 0. Okay, one stable and one unstable fixed points meet and result to result in the disappearance of both the fixed points, right? And this is known as saddle node bifurcation. Why? Because there is a saddle point and a stable node. Saddle point and a stable node come together and disappear. Both of them disappear, resulting in non-existence of any of the fixed points. Or the vice versa is also true, which means that with the increase of the parameter, initially there is no fixed point and suddenly there is a presence of a half stable fixed point which further bifurcates into a stable and an unstable fixed point, then that is also a case of a saddle node bifurcation. B, we'll talk about pitchfork bifurcation. We'll talk about what is a pitchfork bifurcation. So the normal form, okay, so firstly, the pitchfork bifurcation is of two types. One is a supercritical type of pitchfork bifurcation. Another one is the subcritical type of pitchfork bifurcation. So we'll talk about both. So coming on to the first one, which is your super first one, which is a supercritical pitchfork bifurcation. Okay, so for this, the normal form is something of this type. Okay, so if I try to find out the fixed points, what will I get? I'll get okay, which gives x is equals to 0. Okay, so here you can see that for r less than 0, we have only one fixed point, x is equals to 0. And for r greater than 0, we have three fixed points, x is equals to 0 and x is equals to plus minus of under root of r. Okay, so if we try to again make a plot of it, how are we going to do? Okay, maybe I should write on the next page. Okay, so for the first case, when my r is less than 0, how is the plot going to be? Well, it's a cubic equation, so it will be something like this. Okay, and this is my fixed point. So talking about the stability, now we know. Okay, we'll come on to stability later. First, let us just make graphs first. For r is equals to 0, the plot is again going to be something of this type only, with only one fixed point. And here we are going to have three fixed points. Now talking about the stability of these fixed points. Okay, so here, how is it going to happen? It is going to take it like this. And this is going to take my system again towards the fixed point, correct? So both are taking me towards the fixed point, and hence this is a stable fixed point, right? Coming on to the second case, again, from both the direction, the arrow is pointing towards the fixed point, which means that for r is equals to 0 also, where we have only one fixed point, but this fixed point is a stable fixed point, right? Coming on to this, how is it going to behave? So this is going to be pointing towards the fixed point. This is going to be pointing towards the fixed point. This is going to be pointing away from the fixed point r0. Again, away from the fixed point r0 towards the fixed point, and again towards the fixed point, right? So what do we get? We get that my fixed point 0 is an unstable fixed point, while my other two fixed points, minus of under root of r and under root of r, are both stable fixed points, right? Maybe I should write the terminology here only. I can write. So filled dot means stable fixed point, and an unfilled point means unstable fixed point. Okay, this is how my system is going to behave, right? For all the three values of r. Now, if I try to plot this with the value of r, how is it going to be? So if this is my r, initially my 0 is a fixed point, and as soon as I reach r is equals to 0, my 0 becomes an unstable equilibrium point, and there is emergence of two new fixed points that are stable. As you can see, this looks somewhat like a fork, and that is why it is known as a pitchfork bifurcation. Now, the example that I give, like this one, was a supercritical pitchfork bifurcation, and this is what you can see in the buckling of a beam, isn't it? For the buckling of a beam, this is what we are seeing. Initially, my system was like this in an equilibrium state. After that, my system had two options of equilibrium state. One was like this, or another one was like this, right? And this was simply nothing but a pitchfork bifurcation, right? When my parameter changed from small m to capital M, I had two options of equilibrium points. Okay, both were opposite to each other, similar to that of a supercritical pitchfork bifurcation. Now coming on to the second type of pitchfork bifurcation, which is nothing but a subcritical pitchfork bifurcation. So what is going to happen over here? Here the normal form is given as Rx plus x cube. So there it was a minus. For subcritical it's a plus, right? So here what equilibrium points we are going to have? So earlier we saw that my fixed point was plus minus of r, plus minus of under root r, which means that if my r was positive, I had two equilibrium points, and if my r was negative, I had zero equilibrium points. Well, for this case, as you can see, only if my R is negative, then only I'm going to have fixed points, right? For positive value of R, there will be no fixed point, correct? So if we try to plot for all the three cases, what are we going to get? Here we have three fixed points. Here we have one fixed point. Here we have one fixed point. This is for R less than 0, R is equal to 0, R greater than 0. I hope this is clear. We have already done this exercise for the previous case. And talking about the stability again, what is going to happen? Let us see. So for here, the velocity is going to be the away direction. Here also it will be taking it away. Here it will be taking it towards this fixed point. Here also it is going to, okay. Here it is going to take it towards this fixed point. Here it is going to take it away from the fixed point. Here it is going to take it away from the fixed point. Correct? This is what is going to happen, right? So if I see over here, my this fixed point and this fixed point, which is nothing but minus of under root of minus r and under root of minus r. Okay, they both are essentially unstable equilibrium points. While my this fixed point, which is 0, 0, it is a stable fixed point. Correct? Now, as soon as I switch to R0, you see what is happening. Now, this is taking the system away from this fixed point, and this is taking the system away from the fixed point. So now my 0 becomes a unstable equilibrium point, and along with that, the other two unstable equilibrium points has vanished. Right? So what happened is that both the unstable fixed points vanished, and the stable one got converted into an unstable equilibrium point. Similarly is for this also. This becomes unstable equilibrium point. So if I try to plot it with R, the behavior is something of this sort. Earlier 0 was stable, then 0 becomes unstable. This is for R0. And here we have two forks which are of unstable equilibrium point. Right? So if I try to summarize both the cases of my pitchfork bifurcation, where one was my supercritical pitchfork bifurcation and another one is the subcritical pitchfork bifurcation. In case of a supercritical pitchfork bifurcation, here you can see that there was only one stable equilibrium point, 0. As my value of R changed from negative to positive, I had two new fixed points which were stable, and my 0 fixed point became unstable, right? But for a subcritical pitchfork bifurcation, what I saw, for my subcritical pitchfork bifurcation, I had three equilibrium points for the negative value of R, out of which two were unstable and 0 was stable. Now, as the value of R progressed from negative to positive, my both the unstable equilibrium points vanished and the stable equilibrium point got converted into a unstable equilibrium point. And this is also known for causing catastrophic failures, subcritical pitchfork bifurcations, because here you can see that as the value of R is changed, there is the disappearance of any of a stable fixed point. Okay. If my parameter is changing, it may happen that earlier it is at a stable state and after that it just does not find any, it goes into searching of a fixed point but does not get any fixed point and essentially goes causing a catastrophic failure. Okay, me cause catastrophic failures. Okay, I hope it is clear. Now coming on to question number 6. Okay, so the question number 6 says, which among the following material changes its stiffness with the change of electric field? Okay, so as you know that we are now switching.
I have a
Hello?
doubt. Ma'am, I have a doubt. What is the
Yes?
answer of the last question?
Okay, sorry, I forgot to mark the answer. Answer is this, supercritical pitch fog. C. C is the correct answer, as I've
Ma'am,
discussed. Yes?
I have one more doubt. Ma'am, uh, how we point out the direction of arrow, and when you are explaining the graph of x and x dot,
Mm-hmm.
then you have taken the r is equal to 0 or r less than 0, and you have taken the points. Then how you mark the direction of arrows? We moving towards the like.
Yeah, yeah. Okay, see, I explained it earlier also. See, this is how it happens. If I consider this fixed point, like for example, if I consider a case where this is the variation, this is a fixed point. Okay, so here, if I see my x dot. Okay, so if you see that right to this fixed point, my velocity is positive, right? So if my velocity is positive, what is going to happen? If I am standing over here, I'll be going in this direction because my velocity is positive, correct? And if I'm standing over here, since my velocity is negative, I'll be going into the negative x direction. Okay, so this is how arrows are made.
Okay, okay, ma'am.
Okay,
Thank you.
welcome. So coming on to question number 6, which among the following material changes? So yeah, as I was saying that as we are going further in the research field, we have now been working on soft materials, right? So soft materials are essentially important because it has a wide variety of applications, and it gives us wide variety of advantages as well as compared to the rigid materials. Okay. So among the soft materials, then there are materials that are being actuated by external stimuli. Okay, like for example, if I have a rigid material, if I have a, let us say pen, if I have this pen, if I want to lift up this pen, I have to grab it and then apply a force and take it. Or if it is kept on a table and I have to move it, I'll maybe apply a force like this and then move it, right? So this pen is moving because I'm applying force on it. How about talking about the materials that show deformation or they show the change in their shape or size when any external stimuli? External stimuli like electric field, magnetic field, light, or temperature, etc. are applied, right? So depending on that, we have different kind of materials. Like A, we have dielectric elastomer. So what is essentially special about a dielectric elastomer is that for a dielectric elastomer, when electric field is applied across the material, Okay. So when electric field is applied across the material, then it shows reduction in the direction of the applied field. Okay. Reduction in the thickness or reduction in the length in direction of the applied field. Okay. So for example, if I have the material like this, and now if I apply electric field, okay. So this is what we call it as a dielectric elastomer. It shows deformation on the application of electric field. So this is your answer, but I'll talk somewhat about the other two also. So B is your shape, memory, alloy. So what is a shape memory alloy? So these kind of material, they have the ability to remember their shapes. Okay. So they have the ability to remember their shape, and as soon as, like for example, if I have a rod, I deform it. Okay, I change its length and everything. And then I heat it. Okay, it is going to return back to its original shape and size. That is what a shape memory alloy is. It remembers its shape. Okay. So shape memory alloy have the ability to return to its original form when heated. Okay. So when it is at a cooler temperature, it is going to, hello? Hello? डॉम लैब चल रहा है क्या
Yes,
with
ma'am. Your voice is audible.
hello, my voice is audible?
Yes, ma'am.
Oh, okay, I lost my connection. Just wait for 2 seconds, 2 minutes. I'll just again reestablish. Yeah, I think now my screen is visible, right?
Yes, ma'am.
Okay, thank you. Okay. So as I was saying that the shape memory alloys, they have the ability to return to its original shape when it is being heated. Okay. And C is the magnetoactive elastomers. As the name suggests, the magnetoactive elastomers, they are the elastomers that show deformation when a magnetic field is applied. Okay. So if you apply a magnetic field, it is going to show deformation. Along with that, it is also going to show the change in the material properties. Okay. Now I'll try to come to the seventh number question because we are running out of time now. Okay, so the equation of motion of the system is given as like this. So this is a linear system. I've taken this question just to make you understand the concepts. Okay, so this is a linear system. So I can try and write it in a generalized way, like in a matrix form, like x dot, like this. And then we can write it like x dot is equals to a into x. Yeah, this is how I can write. Okay, so coming on to that, how depending upon this equation, given equation, I can find that how the system is going to behave. Correct. So for this kind of a system, if I know the eigenvalues, it is going to tell me system behavior. Okay. So if you people remember that for a linear system, we used to write the solution in the form like C1 e to the power lambda 1 t plus C2 e to the power lambda 2 t, where lambda 1 and lambda 2 were the eigenvalues, right? So if I know the eigenvalues, I know how the system is going to behave, right? So for example, if my lambda 1 and lambda 2 both are real and positive, what is going to happen? If you'll see e to the power something positive into t. So as time progresses, the value of e to the power lambda 1 t is going to increase. It's going to increase, 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 increase in an exponential way, go to infinity, right? Both the directions. So what do I know? I know that my system is not stable. It is unstable. Okay, so my system is unstable, or I should say that my fixed points are unstable. Second is when lambda 1 and lambda 2 both are real and negative. Similar ideology. In the above, it was positive, so it was going out and out and out and out to the infinity. If it is negative, so if you'll see C1 e to the power lambda 1 t, where lambda 1 is negative, what is going to happen? As time progresses, this e to the power lambda minus of some value, it is going to get decrease. It is going to come to a certain value as time goes to infinity. So in this case, my fixed point is stable. Now coming on to the third case where lambda 1 and lambda 2 both are complex. Complex means they are of the form A plus minus iota B, right? Now my A can be positive, My can be negative, right? Iota b means what? Iota b means it is going to have a oscillation kind of a behavior. But the value of A is going to tell whether that oscillation is going to be spiraling in, spiraling out, or a constant oscillation. So if my A is positive, okay, e to the power something positive and plus or minus of iota b. Iota b is going to create oscillation, but this positive value is going to take the system out. So my system is going to behave something like this, spiraling out, right? Spiraling out, going outside. If my A is negative, spiraling in, okay? And if my A is equal to 0, I guess there is a lag between my voice and my writing. Okay. If my A is 0, then what? I have just IB. It means there is going to be periodic oscillation, right? So this is what the case is. So I need to find out the eigenvalues first. So there are two ways of finding the eigenvalues. First is the analytical way, which we all know. Yeah, we all know that we have A, then we'll do minus lambda I, then we are going to have an equation which we have to solve. But it's high time that we should now switch to numerical techniques or maybe use symbolic softwares which will be helpful to get accurate solution. And since we are dealing with non-linear system, it is very important that we start learning a software. And I'm assuming that you people don't know how to use MATLAB. So I will be showing you with this course also that how to use MATLAB. And then I will be telling you that how MATLAB is also useful for simulating of the nonlinear system. So now I'll just switch this off and I'll go to MATLAB. Okay, now I'm going to share my screen. Okay, I hope that my screen is visible. Okay, so this is essentially a MATLAB environment. Okay, we have workspace here. We have this area where we can open our code and we have this command window. So this workspace essentially saves whatever variable we are giving. Okay, and the command window is where we can give the command, and these are the m files, .m files, in which we can write the whole code and run it in a single go. So first two commands that I want you to learn is clear all and CLC. So clear all removes everything that is inside the workspace, and CLC clears everything that's on the command window. So we'll first do clear space all, enter. See, the workspace got cleaned. There's nothing in the workspace now. And then we'll do CLC. Okay. Now, for example, I want to allot a variable. Let us say A. I want to give A a value. So I'll let A is equal to 5 and then I'll say enter. So it will show me the result in the command window and it will also store it in the workspace. Now MATLAB stores everything in an array or matrix form, and so you can write it in an array form. So if I want to make a row vector, I'll write it with space like 1 space 2 space 3 space 4, enter. This makes a row. And if I want it in a column fashion, I'll write it as A is equal to 1 semicolon 2 semicolon 3 semicolon 4, enter. Now this becomes a column vector. Okay. Now I want to, uh, here's my PPT. We were on question, yeah, we were on this question, right? So we had a matrix that we had to find eigenvalues of, which is -3, 4, -7, -2. We'll write it in MATLAB. -3 space 4 semicolon. Semicolon because now we want it in the next line. -3, 4, -7, -2. Enter. See, exactly same. Now we will write, there is a command in MATLAB, EIG. After EIG, in the bracket, whatever matrix you are going to give, it is going to give you the value of the eigenvalues. Okay. So EIG of A. So see, it gave me the eigenvalues. Now, since I have the value of the eigenvalues, what do I have to do further? Nothing. To do nothing now. I have the values of eigenvectors A plus minus IB. Now, for A value, I can see that the value of A is negative. Negative means what? That it is going to spiral in. So, if I again come on the PPT, you see here the option. The system will converge to a point, spiral out with increasing amplitude, spiral in with decreasing amplitude, show constant amplitude oscillation. What is going to be the correct answer? It is going to be C. Spiral in with, this is my correct answer. Spiral in with decreasing amplitude. Isn't it? This is my correct answer. I hope the environment of MATLAB is clear to you all. And I want you to try some things with MATLAB. And if you have any kind of a doubt, I want you to ask me in the next live session, because this time we are getting a bit out of time and I have to complete 2 more questions. So if you have any kind of a doubt in MATLAB, please ask me in the next class. Okay, we'll discuss about it. We'll try to do some questions in MATLAB. It will clear your understanding. Okay, coming on to question number 8. So question number 8, the van der Waals equation is given as, the equation is giving the steady state response of the system is phase plane as initial condition changes from 1, 0 to 2.5, 1. Okay. So I have already made the code actually for the van der Waals equation. See, so there are 2, 3 things that you need to understand that what we are doing. So for a van der Waals equation, see here, it is essentially a nonlinear system, correct? So we have to solve a nonlinear system. So for solving a nonlinear system, we don't prefer going into the analytical way. However, this van der Waals equation, there has been attempts to solve and get the approximate analytical solution, and they have done it very nicely. However, I'm trying to impart you the knowledge of how to solve it numerically so that you are be able to do your questions of week 1 exercise. So this is essentially a second order differential equation. Okay. So for a second order differential equation, we'll use MATLAB's ODE45 command. ODE45 is nothing but a numerical technique of integration. Okay, like we do normal integration, there is a numerical way of doing the integration. Okay, and OD45 is based on the RK for Range Katta fourth order method, which is used for doing the integration. And OD45 is essentially a command that is built in MATLAB to solve the given differential equation using the RK4 method. Simple. What do we have to do? We have to just put in the equation and solve. Okay. So how are we going to put in we have to write the code, right? So firstly, we are defining the function z dot here, and z dot is equals to z2. Okay, so when we are solving through OD45, my OD45 is capable of solving only the first order differential equation, which is u dot. But the given equation is a second order differential equation. So what do we have to do? So we have the ability that we can convert any nth order differential equation into n first order equations. Okay, so we have a second order differential equation. We'll convert it into a two first order differential equations. Simple. We convert it. I have just written the code now. I'll try that make you understand this in the next class because we are running short of time. So here is the code, and when I'll upload the PPT, either you can take the screenshot of this code or anyways, when I'll upload the PPT, I'll give this code so you can practice this, and then you can use this kind of algorithm to solve your assignment problem also. Okay. So z dot is given as z2, which is my first differential equation, and then I have this 1.5 into this. This is my further equation, which is the acceleration equation. Now, what have I done in the first line of the code? I have defined t, which is my time, which is from 0 to 20, and at a time step of 0.1. Okay, so I'll show you. If I define a variable a is equal to, in square brackets, 1 is to 10. This is how it is made. You can see. Okay, so a is essentially a variable which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is from 1 to 10 by default of taking 1 as a step. Okay, but if I specify a step, if I specify 0.1, I take it as 1. Okay, sorry. See, now it is defining a as a variable from 1 to 2 with a step of 0.1. Right? So what have I done here is I have taken t, which is a variable from 0 to 20, okay, and at a time step of 0.01, okay, which is a very small time, and the small time is also required because when we are solving in numerically, if we take a smaller step size, we are bound to get more accuracy, and because you understand we are performing a numerical technique. Okay, so we are dividing the whole continuous form into a discrete form. Okay, so the number of discrete points, when it increases, the uh, relation to the continuous one is actually becomes more accurate. Okay, so we have tried to get accuracy, but see, there is also one thing known as the computational cost. Right. As an engineer, it is my responsibility that I get better accuracy considering the computational cost. Right. Right. So I have to consider the computational burden as well. Okay. So what have I done? I have defined time from 0 to 20 at an step of 0.01. Okay. Next, I have defined the initial displacement and initial velocity as 1, 1. Okay, in the PPT, the first is 1, comma 0. Okay, so my initial displacement is 1, initial velocity, I'll take it as 0. Now I've defined a variable z 0, which is actually the value of z at time 0, which is nothing but an array which has initial displacement and initial velocity 1, 0. Next is t comma z. We have called the OD45 command, and now we are solving this equation. And the fifth line of code is essentially how we are plotting. We are plotting the displacement with time, and then we are plotting the displacement with velocity. Phase plane or phase plot is nothing but the plot in which one direction is your displacement, another direction is your velocity. Okay, now we'll run the code. Okay, so this is your time response and this is your phase plot. Okay, you can see that in the time response how the system is behaving, and in the phase plot you can see that we started from the initial condition this and it went to a periodic orbit. Now we'll change the initial condition 2.5 and 1. Okay, wait, I'll apply a hold on. Okay, so this is the plot we got. The second one is the orange one. So here we can see that in the phase plane, I have two different initial conditions, but the final steady state response is essentially the same curve, right? So this actually is the case of a limit cycle, which I'll be discussing in the further lectures. Okay, and in the time response, if you'll see that the amplitudes of vibration is the same, the behavior is same, the steady state behavior. However, there is a phase lag, right? And that phase lag is essentially because of the change in the initial condition. Closing this and coming to the PPT, we have the steady state response of the system in the phase plane as the initial condition changes from 1, 0 to 2.5, 1. The correct answer is A, remains the same, right? Now coming on to question number 9, which is the Lorentz system. So the equation of motion that has been given is that of a Lorentz system. So see, the nonlinear dynamics are based on the study of some equations that form the basis of the whole concept of nonlinear dynamics. And the Lorentz system is one of those kind of a system. So we'll be taking many more questions on Lorentz system actually. So this is a very basic question. So the Lorentz equation is given as this. The response of the system for initial condition 1, 1, 1 is. Okay. So I've again made the code and we'll just simulate it. So see here, again I have defined time from 0 to 20 and at a time step of 0.01. Then initial displacements are taken as 1, 1, and 1 in all the three directions. Since, see, if you'll see here in the PPT, this is essentially, there are three first order equations, right, which are interlinked to each other, right? So we don't need to convert this equation, okay? We'll just use the equation in the same fashion. Okay, so t comma z OD45. Then we have called the function and then we have done the plot of this and we'll just do it. Here I have defined the equations already and you can try this. I'll put it the snapshot in the PPT. If you have any doubt, then ask me and I'll try to explain you further about how we are simulating the system in the next lectures. So we'll simulate the system. See. This is the behavior that we are getting. Now I don't know what kind of a behavior is this. I mean, by merely just seeing it, I cannot say whether it is periodic, quasi-periodic or anything. Let's do one thing, let's increase the time. Okay. Now I know it is not periodic. That is for sure. Okay, because if it had been periodic, the behavior would not have been like this. But the question is whether if not periodic, then what is it? Is it quasi-periodic or is it what? Okay, so here comes the concept of chaos. Okay, so chaos, as I told you, periodic behavior is always going to be periodic. Okay, quasi-periodic behavior, if you're going to have a very small change in the initial condition, very small, let us say at the power of 10 to the power minus 12, the behavior is still going to be the same because that is not going to bring any kind of error or difference in the dynamics. But when you talk about chaos, chaos is very sensitive to the initial condition. Now, why am I saying that? Let us do one thing. Just apply a hold on first, and we'll simulate again. And now we'll change the initial condition somewhat. See, I have changed the initial condition. How much have I changed? I've just changed 1 to 1.001, right? This is a very small change. Even if I try to add more zeros, see, did you see the behavior? How is the behavior looking to you? Initially, up to this point, the behavior is almost the same for all the three initial conditions. However, after that, you can see that there is a lot of variation in the in the response of the system, corresponding to a very small change of the initial state. Okay, now what? This is chaos. This is something what we call chaos. A aperiodic motion that shows a very high sensitivity towards the initial condition is what we call chaos. Okay, this is not quasi-periodic and not periodic. You cannot find any kind of a periodicity in chaos. You cannot find any kind of a quasi-periodicity. You cannot find any kind of determinacy in chaos. Okay, it is just aperiodic random behavior which shows very small sensitivity to the initial condition. And in the next class, I'll talk about the butterfly effect, which essentially gives the concept of chaos. So chaos is a very delicate kind of a behavior, which we try to avoid in any kind of a physical system. Because you see, in any physical system, there are multiple kinds of error. It has machine error, measurement error, human error, many kind of error. Okay. But if we make a system that is so sensitive to the initial condition, the smallest of the error can cause a very vast change in the dynamic. You see, when I am supposed to have the minimum displacement, I'm having the maximum displacement. What is it going to happen? It is going to cause catastrophic failures, right? So that is why we try to make a system avoid chaos in every possible way. Okay, and that is what is essentially important, that we study the nonlinear system in order to avoid chaos. Okay, further we'll discuss in the next class. I think this is enough for today. We are already done. We have discussed the questions which were important, and I guess these questions will be helpful for you to answer your assignment 1 questions. If you have any doubt, please write it. We'll discuss in the next lecture, and just remind me before the lecture or starting of the lecture that we have doubts, so then I'll try to complete 10 minutes before. Okay, so should I end the session here? Anyone has anything to
How
say?
we can get the access to MATLAB?
Sorry.
How can I get the access to MATLAB?
MATLAB, there is a provision of online MATLAB as well. Apart from that, maybe it's a paid software, however, but your college must be giving some free access to the student. So you'll have to check that.
Okay, ma'am.
Okay. Yeah. Okay, then I'll end the meeting now. Thank you, everyone.